NDVI is Normalized Difference Vegetation Index. It's a spectral enhancement method and widely used in remote sensing. It is based on the principle that the land, water, and vegetation exhibit different reflectance properties in the near-infrared, NIR, and red light spectrum. By analyzing these differences, NDVI provides a quantitative measure for distinguishing and assessing these features. We can calculate the NDVI using the reflectance of NIR and red spectrum from different surfaces. When near-infrared light from the sun strikes vegetation, it is almost entirely reflected. As a result, NIR images of vegetation appear brighter. For example, this is a Google map of the Krishna River Delta. The green areas represent vegetation. In the corresponding NIR image, these vegetated areas appear as brighter pixels due to higher reflectance. Consider the red band reflectance from the same area. It appears dark due to the high absorption and less reflection of red light by vegetation. If we apply the NDVI formula to vegetated areas, the value typically ranges between 0.2 and 1. Consider the same Krishna River Delta. The soil-exposed areas next to the vegetated regions appear less bright in the NIR image compared to vegetated areas due to lower near-infrared reflectance. When NIR radiation interact with dry land surface, some portion of the radiation is absorbed by the land and rest is reflected back. When red wavelength light interacts with dry, open land, some of it is absorbed while the rest is reflected, similar to NIR radiation. The image looked darker in open area in red band. However, the reflectance of red light is lower than that of NIR. When we apply the NDVI formula to open land areas, the value typically ranges between 0 and 0.2. Such dry soil-exposed areas always yield a positive NDVI value because NIR reflectance is slightly higher than red reflectance in these cases. Let us consider water bodies in the NIR band. Clean, non-polluted water bodies appear extremely dark in NIR images because the incident NIR radiation is almost entirely absorbed by the water, with zero reflection. The same water body in the red band appears slightly brighter than in the NIR band. This is because the red light is not completely absorbed by the water body, and a small portion is reflected back. If we apply the NDVI formula to water bodies, the values will range between -1 and 0. This occurs because NIR reflectance is lower than red reflectance in water bodies, resulting in negative or near zero NDVI values. From these different scenarios, we can conclude that NDVI values range between -1 and +1. Water bodies exhibit negative values, typically between -1 and 0. Open land and built-up areas generally show NDVI values between 0 and 0.2. Vegetated areas, on the other hand, display higher NDVI values ranging from 0.2 to 1. Now we shall open the Google Earth Engine code window for writing a code for calculating NDVI. Insert a geometry using the point marked at the area of interest. Since the area of interest is Krishna Basin Delta, we shall change the name of the variable as delta. We shall type the Landsat 9 to get the data catalog. Select the top of the atmospheric data. Copy the code snippet. Assign the code snippet to a variable called L9. Now we shall use geometry to filter the data. After retrieving all the data for that area, we will search based on date. We will create a cloud-based filter to obtain better data from the filtered images. We will take the first image from the list of retrieved data. The section of the code discussed above has already been explained in detail in a video on the same channel. The link is provided in the description. Next, we will display the true color composite of the image. First, we will set a zoom level using the Map Center Object function. Then, using the Map Add Layer function, we will display the image stored in the L9 variable. This part of the code, which displays the true color composite, is explained in detail in a previous video on the same channel. The link is provided in the description. Run the code to get the true color composite. We know that the formula for NDVI requires both the NIR and red bands. Therefore, we will select only these two bands from the image. The .select command can be used to select a specific band from the set of bands. Here, band 4, red, and band 5, R, are selected and assigned to two different variables. Here, NIR and red are two variables. L9 is the Landsat 9 image containing 11 different bands. The .select operation will isolate band 5, NIR, and band 4, red for further use. We will apply the NDVI formula now. Here, the .subtract is equivalent to minus operation. Similarly, .divide is for division and .add for addition operation. We will use the map.addLayer command to display the NDVI image. Since the range of NDVI values is from -1 to +1, we will specify the pixel value range for display as -1 to +1. Run the code to display the NDVI image. We can see the names of the images in the layer dropdown. Instead of writing formula, we can use built-in function to calculate NDVI. The normalized difference function is a built-in function that directly uses band 5, NIR, and band 4, red, to calculate the NDVI. No need to select the bands and declare variables in this case. We can use function directly here.